can hear. Yeah.
Okay, so first of all, I'd like to thank the organizers and Sayantan for inviting me to give this talk, and I'm happy to see you guys here. Although I cannot actually see your faces, but I can feel your existence from your name list of the names. And so today I'm going to talk about two topics actually. One topic is going to be the chiral magnetohydrodynamics. I'm talking about this because this is a requested title from the organizers, and I kind of try to fit in the program of the workshops. Maybe this is a tendency of Japanese people, but so first I'm going to talk about Chiral MHD. And second, in the second part, I'm going to talk about something called higher form symmetries and associated Nambu-Goldstone modes. And so apparently, at first sight, those two topics kind of look irrelevant. But so actually, there's a interesting connection, and the connection is going to become apparent in the course of the talk. So let's just start. So the system that we are going to be talking about is the system of the massless fermions. And as we learned in the previous talk, we can associate chiralities to the massless fermions. So they are either right-handed or left-handed. And those handedness or chirality of the fermions is conserved only classically. And once that we take into account the quantum effect, the conservation of the chirality is violated. And so this is the so-called chiral anomaly, and the extent of this violation of this chirality flipping can be quantified by this chiral anomaly equation. So here this JA is the actual current, which is a difference between the right-handed fermion current and the left-handed fermion current. And its divergence is, has some source time, which is quantified by E.B. So those are the electric and magnetic field, and this coefficient is given by this expression when those fermions are coupled to the abelian electromagnetic field. And this chiral anomaly is very physical and responsible for the process of, for example, the spiral decay into 2 photons. And so when you think about some macroscopic system that consists of massless fermions, there's some macroscopic, it turned out that there's going to be some macroscopic transport effect associated with this chiral anomaly, and this is called the chiral magnetic effect. And it can be summarized in one equation. So here, mu A represents the actual or chiral chemical potential. So when this is non-zero, there's an imbalance between the number of the right-handed and left-handed fermions. And if you apply magnetic field in this kind of material, there's going to be a generation of the electric current. So this is chiral magnetic effect. And compared to the conventional transport effects, there are some notable features. One is that this is a dissipationless transport phenomenon, by which I mean that there's going to be no heat production associated with this current. And another interesting feature is that transport coefficient that is here is universal, and it doesn't depend on the details of the matter. And there are a number of physical systems where such effect is going to be happening. And so actually, several years ago in 2016, there was a first report of this experimental observation of the chiral magnetic effect in Dirac metals, and there are dozens of follow-up experiments afterwards. So this effect is physical, that theoretically it should exist, and they are experimentally already verified. And the problem that we are going to think about is its interaction to the with the dynamical electromagnetic field. So suppose we have some chiral fluid in which there can be some chirality imbalance, and when that happens, there's a current inside matter, this matter, which is proportional to the magnetic field. And if this current flows, then that is going to, in turn, modify the configuration of the electromagnetic field through basically the Maxwell equation. And when that happens, and with this modified electromagnetic field configuration, that is further affecting the time evolution or current evolution inside this current fluid. And so those are the coupled system, and the Chiral MHD is the basically the low energy, effective theory that can describe the coupled system of the chiral fluid and electromagnetic field in a consistent manner. And there are certain number of physical systems where this theory can be useful. And so we're going to be talking about this chiral and non-chiral MHD. And let me remind you what the hydrodynamics is. So this is hydrodynamics is effective low energy theory, and this is that it takes into account only the massless degree of freedom, and it's basis on conservation law and also the derivative expansion. And the degree of freedom of this theory is twofold. So one is conserved charge densities. For example, when the particle number is conserved, the particle number density enters as a degree of freedom. And there's also energy momentum conservation and so on. So this consists of one class of the hydrodynamic variable, and another class of hydrodynamic variable is the Nambu-Goldstone modes. So that appears when continuous symmetry is spontaneously broken. And so these are both, leads to massless or gapless degree of freedom. So those are important degree of freedom at low energies. And we will refer to these degrees of freedom as hydrodynamic variables. And time evolution, for example, of the conserved charge density is given by the conservation law, like this. And the current, and here the current is represented as a derivative expansion in terms of the hydrodynamic variable, and that is going to constitute equation motion, which is solvable in principle. And the magnetohydrodynamics is actually such theory. The hydrodynamic variables associated with MHD are basically the energy density and fluid velocity. They are associated with conservation of the energy and momentum. And there's also another degree of freedom, which is a magnetic field. So here I've defined the covariant electric and magnetic field by contracting the field strength tensor with fluid velocity in this way, and F tilde is the Hodge dual of the field strength tensor. And so here we have this magnetic field as a hydrodynamic degree of freedom. And so I'm going to detail this on later, but so this magnetic field can be also considered some sort of conserved charges associated with something called U1 one-form symmetry. And so on this point, I'm going to talk about later. And the equation motion is given by the conservation laws of the energy momentum tensor. And so this one is just a Bianchi identity, but we can view this as some sort of a conservation law. And so this is organized, this theory is organized as a derivative expansion. And let's look at the zeroth order, the behavior of the zeroth order theory, and which is called the ideal MHD. And a notable feature or characterizing feature of this ideal MHD is that there's going to be no electric field in the fluid frame. So basically, if there's some fluid which is moving, and if you are moving with the fluid, and you're going to feel no electric field. So this is because if there's some electric field, there's going to be charge, redistribution, and that is going to cancel the original electric field. So if you looked at the long time behavior, you won't be seeing any electric field. So this is what it means. And so this situation corresponds to the large value of the electrical conductivity. So the constitutive relation at the zeroth order of ideal or magnetohydrodynamics is given in this form in the weak magnetic field limit. It takes this kind of form. So basically, they are characterized by the fluid velocity and also some magnetic field like this. And we also have some corresponding constitutive relation for the field strength tensor. And so we were talking about the chiral MHD, and the modification coming from this chiral part is that we are going to have another degree of freedom, which is denoted by Na. So this is the actual charge density, and so equation of motion is given by this conservation of the energy momentum tensor and also Bianchi identity. And we also have to take into account this anomaly equation for the actual current. And so in this work, we have shown that by requiring the second law of the thermodynamics, we can get the constitutive relation that includes the contribution coming from the chiral magnetic effect. So let's look at some feature of it. If you look at the zeroth order in the derivative expansion, so the constitutive relation is basically the same as that of the ideal MHD with the addition of this part of the actual current. And there's no contribution coming from anomaly or chiral magnetic effect. So this is kind of natural because I've said that in a fluid frame, you won't be feeling any electric field. So this part is going to be vanishing. So the actual current is conserved to this order. So there's no anomaly coefficient appearing in the equation of motion. So there's no effect coming from the anomaly. And if we can further go further and consider the first order corrections in the derivative expansion, and then we can get the usual contribution coming from the bulk and shear viscosity, and there's also first order contribution to the electric field, and which takes this kind of form in the limit of the weak magnetic field. So those are the conventional contribution. And in the case of chiral MHD, we have an additional contribution appearing in this term. And here, this sigma v is defined as the anomaly coefficient times the chiral chemical potential. And sigma here is the usual electrical conductivity. So I forgot when I started my talk. My talk has started around 6:40, right?
Yeah, it was, yeah.
Okay.
2 minutes.
Okay, so here in the first order term, we have found this contribution coming from the chiral magnetic effect. And so this is the contribution to the electric field. And accordingly, we have an energy momentum tensor and the field strength tensor, which gets contribution coming from the first order term of the electric field. And so to the first order, the equation of motion is given by this expression. I forgot to write down this actual part, but so those determines the dynamics of the system to this order. So I'd like to discuss some physical picture of what is happening in the system here. So if we look at the zeroth order part of the energy momentum tensor, and if we look at the spatial part of the energy momentum tensor, which is just a stress tensor, and it takes this kind of form. And if we take the spatial divergence of this quantity by multiplying partial I, we are going to get the force acting, on the system. So the force can be written in this form. So there are two contributions. In the first term, so suppose there's a magnetic field line, and there's a tangent vector to this field line like this, and there's a normal vector, which is in the direction of the change of the tangent vector. So tangent vector is changing in this direction, so normal vector is in this direction. And this is called the binomial vector, which is proportional to the t cross n. And so here the kappa is the curvature of this magnetic field line. So this first term means that when there's a curvature, so when this field line is bent in some way, then there's going to be some force in the direction of the normal vector, which is in this direction. So this is nothing but the restoring force of this magnetic field line. So it when it's bent, it tries to straighten its shape. And if you look at the second term, so this is the gradient in the perpendicular direction to the magnetic field direction. So this is non-zero when there's some dense region of the magnetic field line and some sparse region of the magnetic field line. Then there's going to be a force, in this kind of direction. So it represents some the pressure coming from the magnetic field. And so one interesting feature of the MHD is that something called the frozen in of the magnetic field lines. So there's some fluid, and fluid is pierced with those magnetic field, something like this, and they are kind of stuck together. So if you pull this B field line, the fluid is going to come with you. So they have to move together like this. So then for example, if we consider this kind of situation where a magnetic field line is bent, then as I said earlier, there is going to be a force in this direction to straighten the magnetic field line. But so it carries this piece of the fluid, so it acquires a moment of inertia. So that is why it starts to oscillate in this direction, and this oscillation is going to propagate along the direction of the magnetic field. So this is nothing but alpha wave, and its characteristic dispersion relation is given in this form, where this velocity is given in this direction. So this energy is proportional to the momentum along the magnetic field line. And we can further include the dissipative effect. And when there's a dissipate, so if we go to the first order in derivative expansion, there's some contribution coming from the shear viscosity and also the electrical conductivity. So basically, in the presence of dissipative effect, like shear viscosity or electrical conductivity, there's going to be a damping of the amplitude of the alpha wave because it comes with this imaginary part. And if we consider further the chiral MHD, there's another contribution, which is essentially coming from the effect of the chiral anomaly. And this term is proportional to anomaly coefficient and also the chiral chemical potential. And so here we are taking the momentum to be proportional to the magnetic field, and the S here indicates the so-called helicity of the mode. And so basically this takes plus minus 1 and represents the right-handed or left-handed mode. So as you can see from here, the sign is going to be positive and negative for either positive or negative helicity modes. So which means that there has to be some, instability in either modes. So for example, if suppose this chiral magnetic conductivity, which is anomaly coefficient times chiral chemical potential, is positive, then the negative helicity mode is going to decay. But the mode with positive helicity is going to multiply exponentially if the momentums satisfy certain condition. If this momentum is smaller compared to some critical value, and its critical value is given in this kind of expression. So we observe some instability at the small k mode, which means that small k mode means the corresponds to the large scale structure. So that is why, this instability leads to the formation of some large scale structure of the magnetic field in a chiral MHD, and which is also discussed in the previous talk by Naoki very nicely with very nice movies. So this is some feature of the chiral MHD, and I'd like to look at this Bianchi identity, and it sort of looks like a conservation law, right? And so this can be actually regarded as the conservation law of some charges associated with some general symmetry called a one-form symmetry. And I will discuss what this one-form symmetry is. So those, generalized symmetries are called higher form symmetries. And this is a generalization of symmetry in some sense. So in the case of a usual symmetry, there's some field which are transformed under certain symmetry and with some representation like this. And the defining feature of the so-called higher form symmetry is that the charge object under this symmetry can be extended object. So they are referred to as p-form symmetry, where p is an integer. And for a p-form symmetry, the corresponding charge object is a p-dimensional object. So for example, if we consider the zero-form symmetry, the charged object is just a zero-dimensional object, which is the point. And this corresponds to the ordinal symmetry, where the charged object is local field, which is defined on a point. And if we consider, for example, one-form symmetry, the corresponding charged object is defined on a one-dimensional object like this. And there are, and there are higher, even higher form symmetries too. And so if we consider the U and P form symmetry, the corresponding charge object that I wrote here is defined on some p-dimensional object. And since it's a U symmetry, it is the symmetry to rotate the phase of this field. So this is one example. And this higher form symmetries, the concept of higher form symmetry is, kind of useful because it provides us with, unifying viewpoint. So many concepts that we are familiar with in the case of linear symmetries can be sort of generalized to those higher form symmetries. And for example, those symmetries, higher form symmetries can be used to characterize the phases of matter. So they can be spontaneously broken, and that breaking pattern can be used to characterize the phase of some matter. And for example, so when a discrete higher form symmetry is spontaneously broken, there appears something called topological orders. So conventionally, those topological orders are considered to be non-classifiable in terms of the symmetry breaking pattern, but there are certain type of topological orders are seen as a consequence of the spontaneously broken higher form symmetries. And so there's a continuous higher form symmetry, and when they are spontaneously broken, there appears Nambu-Goldstone modes, and so the Nambu-Goldstone theorem is extended to those higher form symmetries, and actually the photons are considered to be Nambu-Goldstone mode associated with the breaking of a U1 one form symmetry, and so when there's a symmetry, we can consider the gauging of the symmetries by introducing some external gauge field. And when there is an anomaly, then we can use this as a constraint of the possible low energy physics, because this, anomaly should be, conserved, at low energies as well. And there's a very nice, formulation of the MHD using those the languages of the higher form symmetries, pioneered by the next speaker, I think. So I'm gonna now talk about the problem of the counting of the number of the Masters mode or Masters Nambu-Goldstone modes when the higher form symmetry is broken. I have enough time, right? So
yes, you have.
Yes. Thanks. So it's kind of obvious, but the spontaneous symmetry breaking is a very important concept in virtually, every field of physics, I guess. And one reason why those spontaneous symmetry breaking is important is that it's often lead to some low energy degree of freedom. For example, so when some discrete symmetry is broken, so there appears some domain walls and so on. And when a continuous symmetry is spontaneously broken, we're going to have massless or gapless excitations, and they are the Nambu-Goldstone mode. And there are numerous examples of this. If we look at QCD, we can regard pions as Nambu-Goldstone mode associated with the chiral symmetry breaking. And if we look at the condensed matter physics, so there are magnons which appear in a magnetically ordered matter. And if you look at the superfluid, then there are massless, superfluid phonons. And those so those excitations are regarded as Nambu-Goldstone mode associated with some internal symmetry breaking. The breaking of some internal symmetry. And we can also have some lattice phonons when atoms form a lattice like this. And there's something called a kelvon. So this is basically the vibration of a vortex string, which is propagating along the vortex. And so those are, we can regard those as massless mode associated with a breaking of a space-time symmetry, because in the case of phonons, lattice phonons, the continuous translational symmetry is broken to discrete ones. And so now that the photons are regarded as a Nambu-Goldstone mode associated with a breaking of the higher form symmetries. And so it is an important problem to constrain the properties or the numbers of the those massless degrees of freedom based on the symmetry breaking pattern, because they are the most important degree of freedom if we are interested in the low energy physics. And we can identify the number of the appearing Nambu-Goldstone modes in some situations. So suppose that there's some internal symmetry G, which is broken to H. And if we assume the Lorentz invariance of the system, there's actually a one-to-one correspondence between the Nambu-Goldstone mode and the broken symmetry generators. So there are the number of the massless mode appearing is going to be the same as the number of the broken generator in Lorentz invariant systems. And the dispersion relation is also given by linear ones, which is also due to the Lorentz invariance. But this is not, true once we consider a system which is not necessarily Lorentz invariant. So the most plain example of this, the lack of this one-to-one correspondence between broken generator and massless mode is provided by the magnets. So suppose we consider some Heisenberg model whose Hamiltonian is given something like this. And if the parameter J here is positive, then the spins try to be anti-parallel to each other in order to lower the energy. So the ground state is going to be something like this. And if the parameter J is positive, not negative, then in order to lower the energy, it's better to be in the same direction. So the ground state is going to be something like this. And if you compare those two situations, so actually the symmetry breaking pattern is the same. So originally there is a spin rotation SO3 symmetry, and this is spontaneously broken to SO2 part, which is rotation along the axis. So the number of broken generator is 2. And indeed, in the antiferromagnet, there are 2 massless modes, which both have the linear dispersion relation. But in the case of ferromagnet, there's only one massless particle appearing here, and it has the quadratic dispersion relations. So although symmetry breaking pattern is the same, the consequences are somehow different between those two examples. And this, change or difference in the behavior of the dispersion relation is relevant when we consider this thermodynamic property of the system. For example, when we have some massless particle with this dispersion relation, then the heat capacity C is going to behave as a function of temperature like this. So where this D is the spatial dimension, so N is the number appearing here. So the T dependence of the heat capacity is going to be depend on the dispersion relation. And so this is one example here. So below the, some temperature, the system is antiferromagnetic, and it shows nice scaling, linear scaling with the temperature. And so with that, we can kind of infer that the system is effectively one-dimensional. So those dispersion relations are important in characterizing the thermodynamic behavior of the system. So we wonder, so where does the difference come from? And the important difference is that the lack or an existence of the magnetization. So in the case of antiferromagnets, since they are aligned like this, there's no net magnetization in some direction. But in the case of ferromagnets, there's since they are aligned in the same direction, the magnetization density is non-zero. And this magnetization, if we take this direction, this order direction as z, then SD, the expectation value of the SD is non-zero, and it can be written as a commutator of the SX and SY. So it looks like some charge commutator is playing some role here. And in fact, I mean, those people studied that if we compute the charge commutator of the broken charges, and if it's the orbital components are commuting, then the number of the Masters mode is going to be equal to the number of the broken generator. And the correct relation between the number of Masters mode and the number of the broken generators in a non-relativist system is proposed in 2011, and it is proved in the next year. So the number of Masters mode is given by this formula. So this is a expression. So this is the matrix defined by the expectation value of the charge commutator. So those are the broken generators. And since this is an antisymmetric matrix, its rank is always even. So this is going to be integer. And moreover, there's some classification of the Nambu-Goldstone mode into type A and type B. And type B energy modes are defined as modes which contribute to this pairing. And those modes typically are shown to typically have a quadratic dispersion relation, while the mode which do not contribute to those pairing has a linear dispersion relation. And since we can see that in the previous example, we can see that this is satisfied because in the case of ferromagnet, the number of broken generator is 2 minus the rank of this matrix is 2. So this is 1. So this is, and in the case of anti-ferromagnet, so there's no commuting charge. So this part is 0. So we can see that in this example of the magnet, this relation is satisfied. And this, formula can be understood, naturally from the viewpoint of the effective field theories of the energy modes. So we consider the effective theory up to the second order in fields and the derivatives, because we try to consider some dispersion relation, which is the property of the free theory. And it can be, in general, written in this form. So here, those pi a's so those are a transformed field under symmetry A. And so there are terms with second order time derivative and second order spatial derivative. And because of the lack of the Lorentz invariance, there can be also a term with a single time derivative like this. And here, this matrix rho AB can be taken to the antisymmetric matrix because the symmetric part is just a total derivative and doesn't contribute to the equation motion. And so we can, so there are a number of pion fields, and let us classify them into two classes. So there are pion modes which do not contribute this pairing. And for those pions which do not contribute to the pairing, the derivative starts with the second order, and this is basically the same as the situation in the presence of a Lorentz invariance. So those modes create one physical mode per one broken generator. But on the other hand, so there are a certain number of the energy mode field which contribute to those pairing. And if you look at this, for example, if you compute the canonical momentum corresponding to this guy, and that is going to be given by this expression basically. So one pion is canonically conjugate to another pion if you look at this sector. So because of this pairing, two modes is going to represent one physical mode. I mean, for those modes. So there is going to be only one half mode. I mean, per broken generators. And so the number of the energy modes, energy fields, which contribute to this pairing is given by the rank rho. And the rest of the number of the rest of the pion fields is the basically number of the broken generator minus rank rho. And in order to count the total number of the massless degree of freedom, we can multiply 1/2 to its number and also 1 to this number, and we are going to get this result that is presented in the previous slide. And this rho can be shown to be actually kind of proportional to the charge commutator, like this. So this confirms the formula that I showed in the previous slide. And so the Nambu-Goldstone mode appears also for the higher form symmetries, as I told you earlier. And it can be the spontaneous breaking of some higher form symmetry can be also diagnosed by looking at the one-point function, basically, of some charged object. And if it obeys perimeter law or Coulomb law, it is considered to be a broken symmetry. And indeed, the photons are considered to be Nambu-Goldstone mode associated with the U1 form symmetry. And then the immediate question is how many physical Nambu-Goldstone mode that we want to get when higher form symmetries are broken. And is there any, another question is there any role of the charge commutator in the number of in counting the number of the energy modes? Because there has been some study where some non-commuting zero form and one form charges leads to the reduction of the massless mode. So it may be also playing some role in counting the number of the massless modes. And so we have obtained the general formula to count the number of the massless modes for broken high form symmetries. So let me tell you the assumption. So we are considering the spontaneously broken internal symmetries, which can include the higher form symmetries as well as the zero form symmetries. And we consider the capital D-dimensional Minkowski spacetime. And Lorentz symmetry can be there, but it doesn't, have to be respected. So it can be non-relativistic systems. But we still assume that the translational, continuous translational symmetry is unbroken. So those are the assumptions, and here we have used the label A to as a label for PA form symmetry. So there can be different form symmetries in the other broken generator. So this is a summation of the broken generators of PA form symmetry, and so this is just a binomial coefficient. And so there's also some second term here, and there's a instruction to compute this quantity. So when we restart the broken generators and compute this charge commutator, so we have to restart the symmetry generators, which takes into account also the how to place them, the meaning of which I'm going to explain. So in the case of ordinary symmetry, the zero form symmetry, the conserved charge is integrated over some volume. So, and this is going to be the generator of the symmetry. But for a higher form symmetry, the dimension of the symmetry generator is going to be less than the dimension of the space. So there are a number of ways to place symmetry generators. For example, if we consider the one form symmetry in 3+1 dimensional spacetime, then the symmetry generator is 2-dimensional. So it's something like a sheet. And so there are basically 3 ways to place this sheet inside 3 spatial dimensions. So we can place it this way, like this, or we can also place it this way, or we can also place the sheet this way. And there are 3 independent directions along which we can place this sheet. So this independent way of placing the generator should be also enumerated in computing the charge commutator here. Then that is going to give you the number of the massless mode that you are eventually getting. And so the formula we have obtained is a natural generalization of the case of the zero form symmetry, because if we assume that all the symmetries are the conventional zero form symmetries, then PA is 0 for all A, then this is just 1. And then we are just counting the number of the broken generator by this summation. So this formula reduces to the previously known results for the case of zero form symmetries. Then, so let us look at some very simple example. So in the case of photons in 3+1 dimensions, which is our current world, and the broken symmetry is a U1 one-form symmetry, and using this formula, if we plug 1 here and the code 4, then we want to get the number 2, which is basically the same as the number of physical photons that we are observing in our daily life, I guess. And as a slightly non-trivial example, we can consider photons in the presence of the gradient of theta angle. So this kind of system, and it's has been discussed. And it's this kind of system, and its relation to some non-relativistic dispersion relation has been discussed by Yamamoto. And its Lagrangian is given by this form. So this is just a Maxwell Lagrangian. And there's also some theta term, but this theta is actually a space dependent. And so it has some gradient, which is a constant vector. And so in this system, just like the maximum theory, the broken symmetry is a U1 form symmetry. And we have the conserved charge corresponding to this symmetry. And we can compute the commutator of charges supported on a different sheet, and its expectation value is going to be non-zero when there's when the gradient of the theta is non-zero. So if we picturize the situation, so there are conserved charges supported on this sheet 1 and sheet 2, and there's some intersection which is one-dimensional, and so this non-zero non-vanishing expectation value is written as an integral over this one-dimensional integral of this gradient of theta over this intersection region. So now that we have independent generators in 3 directions, as I mentioned before, so there are 3 ways to place this kind of sheet in 3 dimensions, 3 spatial dimensions. And if the commutator matrix can be written in this form, and since the rank of this matrix is going to be 2, the number of the massless mode is going to be 1 according to this formula. And we can actually solve the equation motion and explicitly obtain the dispersion relation. And indeed, so we observe the one massive mode here. So this is a omega squared as a function of the momentum, and this is expanded in the small k. And there's also a massless mode here. And the dispersion relation seems to depend on the direction of the propagation and its relation to this constant vector. If we look at this part, if the propagation direction is parallel to this vector, then it shows a quadratic dispersion relation, but for other generic angles, it shows a linear dispersion relation. So unlike the case of the zero-form symmetries, it's kind of difficult to say something, I mean, in general, in the case of higher form symmetries, about the possible, dispersion relations. And so lastly, I'm going to comment on how to derive this formula. So what we have done is to construct some effective field theory of the Nambu-Goldstone mode associated with the breaking of higher form symmetries. So this is, so in the case of zero form symmetry, this is well known, and so there's a well-known prescription to write down the effective theory, of the Nambu-Goldstone mode, for example, using the coset construction. And in order to extend it to the case of a higher form symmetries, so we have extended the method of this construction, coset constructions, and by writing down this effective field theory of those modes, and using this effective Lagrangian, we have counted the number of the physical massless modes. So this is basically it. And so that's what I wanted to say. So thank you for your attention.
Thanks, Yuji, for sharing your latest works. and we have already 2 questions regarding your work. So the first question is by Samapan. He was asking, does CME contribute to the entropy generation?
So it doesn't. So it doesn't lead to entropy production, at least when we consider some chiral matter and applying the magnetic field in this matter. So there's no heat generation, and hence there's no entropy generation there.
Yeah, okay, thanks from him. And the second question is by Ayan. So Ayan, would you like to ask him directly?
Hi, Yuji. Nice talk. Actually, I had a question about in the very beginning, you said that when we were discussing this number of Goldstone bosons, you said that we had this expectation value of the commutator of the broken generators. Now, how do we see that this expectation value, that this matrix should vanish when we have Lorentz symmetry? How do we directly see this?
So the way to say this is that if this is non-vanishing, then that is violating the Lorentz invariance already.
This is, I think,
so for example,
yeah.
If you have some magnetization, then it has some special direction in the space-time, right? So this commutator can be non-zero only, when there's no Lorentz symmetry. Once you assume Lorentz symmetry, this should be vanishing.
Yes, I understand that. But what if the symmetry is internal symmetry, not a space-time symmetry? So how do we see that this matrix has to vanish?
Yeah, I think this matrix should vanish once you assume the Lorentz symmetry, because in the case of zero form symmetry, this is integrated over some volume, and there's some commutation relation, and so this is essentially proportional to some volume integral. And so some volume integral is not Lorentz invariant concept, right? So we have a space and time, and so we have space and time, and if you have some volume integral, it's a line in the space-time. So this is going to, if this is non-zero, then this is going to break the space-time Lorentz symmetry.
Well, the charges are time independent, right? So why this kind?
Yeah, charges are time independent, but there's no rotational symmetry, right, in space-time direction. The symmetry between space and time is broken by drawing a line here.
Okay, so you're saying that because you have to choose a hypersurface where this should not vanish, so then this breaks Lorentz symmetry.
Yes.
Yes. Okay, thanks. Okay, so I have a follow-up then. Regarding this higher form symmetries, is there a possibility that that the symmetry breaking vacuum is Lorentz invariant too? And in that case, can you simplify your theorem? The number of is it becomes? Can you make a more simpler?
Yes. So in the presence of Lorentz invariance, so this part should be vanishing. So in the presence of Lorentz invariance, only this part remains. This part is going to be zero.
And the dispersion relations then become the Lorentz invariant too, I guess. Then
yes. Yes.
Yeah. So the case of the photon is one example then, I guess. The case of
Yes.
the U1 that we discussed. Okay. Thank you.
Yes.
Thank you. Thank you. Yeah.
We have another question from D. Lun Young. Would you like to ask the question directly or?
Yes, okay, Yuji. Thanks for the nice talk. Just have a very naive question. So I just wonder, could we have the same story for the local symmetry breakings to have the, like, for example, this type B's, now it becomes the gap Higgs bosons, yeah?
I'm not quite sure I understand your question. So what do you mean by type B Higgs bosons?
No, I mean, just, well, that I thought that you only have this, now this is the only this gapless mode, right?
Yes.
So just wonder that, could we have that also this massive bosons is in such a case? Yeah, but with
So I guess you're asking, we have some similar formula, I mean, similar phenomena
right,
to
right,
the
right.
Higgs
Similar
phenomena?
formula for the Higgs mechanisms. Could we?
So yes, so we can have some Higgs mechanism. So the Higgs mechanism is given by some covariant derivative, right? And if this photon is dynamical, then I mean, so there's some, I mean, would be energy mode field, which is some scalar field, for example. And when it's coupled to a dynamical electromagnetic field like this, then so this guy is basically, I mean, eaten, right? And similar thing can occur for higher form symmetry too. So if, for example, this when this is a preform symmetry, then if there's some dynamical p+1 form gauge field, then essentially the same thing as the Higgs mechanism is going to occur.
I saw that Dilum asked the symmetry breaking associated with type B would be energy mode, and that may not be higher form symmetry, or can be higher form symmetry, but the case for type B would be energy mode.
Yeah, I think there has been some studies, right, for the zero form symmetry case. So I think what's going to happen is that, I mean, when type B appears, there's also some massive mode, and those massive mode are also kind of eaten by the gauge field when they couple to the dynamical gauge field.
So the counting rules is still similar to this. It's the same as this case.
But so what is the counting rule in the case of the Higgs mechanism?
No,
So
I mean,
yeah,
well, in such a case, do you still have the same Higgs bosons? Like in the Nambu-Goldstone cases, you have found that the two types of the Nambu-Goldstone bosons, in a sense. Or may I misunderstand something here? Maybe.
So when Higgs mechanism occurs, there's only massive degrees of freedom, right?
Right, yeah, but I wonder in that massive degrees of freedoms whether the counting rules could also be changes when depending on the systems.
Well, yeah, so it, I guess, depends on what you want to count, I guess. And I think what has been discussed before is that, so there are systems which has type B energy modes. And in the case, there are also some massive modes. And when it's coupled to the, I mean, dynamical gauge field, so In relation to those massless modes, the massive modes are also eaten by the gauge field, and that is going to constitute the massive vector field. And I guess similar phenomena can be possible in the case of higher form symmetries too.
Okay. Yeah, okay, I see. So even in the zero form symmetry that it could happen. Okay, so then yeah, okay. Yeah, thanks.
I see no further questions in the chat box. So yeah, so thanks Yuji for kindly agreeing to give a talk, and we end this session now and we reconvene after 40 minutes.
Thank you.
Thanks to all our speakers.